And then also, if you go, I've shown this to you before, but if you go under video resources, you'll see old exams. This is a nice resource because it allows you to see what the exams are going to be like. They'll be different from this, but they'll be very similar. And you can print out the exam. There's an exam in your workbook that we'll do occasionally in class. And then you can also see video solutions for the exam. It's just me working through the exams. Goodness. And so every time we have an exam, I'll post a solution to it so you guys can review what the right answers are. But these are great practice for the exam that you'll be having in this class in a couple of weeks, I think. And then also the screencast. I've placed this online. Oh, that's not it. I'm sorry. Class sessions, our phys101 forum class sessions. These are just our time in class together. So if there's something that you missed in class and you want to go back and catch it, then you can go here. Sometimes the audio is not real great because I just have a little desktop microphone, but it's usually okay for you to just go back and find a few things. Or if you missed class one day and you want to see sort of how far we got, then you can use that as a resource. But also, use people that you know in the class. And if you don't know anyone in the class, then get to know somebody in the class. It'll help you a lot in the class. Okay? Have any questions about those resources? No? I pointed them out before, but often students sort of get lost in the hubbub of the first week. We're not going to generally spend time on the homework in class. We'll go on to Chapter 2. So Chapter 2 is on motion in one dimension. This is called Kinematics. Kinematics is the study of motion. And we're going to sort of camp out on kinematics for a few chapters. We'll have this chapter, which is on one-dimensional motion, where we'll begin to explore some of the predictive nature of physics, especially as it pertains to how things move through space and in time. And then in Chapter 3, we'll begin to look at two-dimensional kinematics. So we'll use some of that trigonometry that we learned in Chapter 1, or that you learned in high school, or wherever it is you learned it, and we'll look at vectors and how we can split up vectors. And then in Chapter 4, we'll see some more kinematics as we do Newton's laws. We'll, in fact, see kinematics even into next semester at various times. So a lot of what we do will build upon itself, and you'll see the kinematics all throughout the rest of the year. Whenever we're working kinematics problems, we need to set a frame of reference. That just means that we need to set the coordinate system. And define the origin. You're going to do this a lot as we move through chapters 2, 3, and 4, where we develop our frame of reference. What is the space that we're working in? So for example, if we have a car that's moving with a certain speed and we want to know, so we want to be able to describe its motion through space, then we'll set a coordinate system. We'll say, well, that's my y coordinate and this is my x coordinate, and where that car is, that's our x equals 0. It's just laying down a coordinate system on your space, okay, the space where you're working this problem. In kinematics, we're going to have 3 different things that we'll consider, and we'll go through and define each of those here. That's displacement, velocity, and acceleration. Displacement, velocity, and acceleration. Often with displacement, we use a variable like x or y to describe the displacement. X if it's horizontal, y if it's vertical. With velocity, we'll use a v, and with acceleration, we'll use a lowercase a for acceleration. So let's just go through and define what these are: displacement, velocity, and acceleration. Displacement we define as delta x, where delta is our Greek letter delta. It simply means that it is a change in something. So it's not like it's a new variable. It just says that we want to know what is the change in x. What is the change in our position, where x is our position. And we're going to have a final position and initial position. So our displacement will be the difference between the final position and the initial position. Let's think about this. We'll watch the Seabiscuit clip. You ever seen Seabiscuit? No, it's getting a little dated, isn't it? But if we have, say, say a horse going around a track. This is our horse. And he races around the track all the way around. What is the horse's displacement? Well, the first thing that we'll do is we'll describe the coordinate system, develop our frame of reference, and we say that that is our initial position. So our x initial, we'll call that 0. Almost always it's going to be our initial position will be 0. And our final position, as he goes around the track and then comes back, what is our final position going to be? It's also going to be 0, just because he's returning back to this original position. So our x final will also be 0. These are both in meters. And so our delta x then will be x final minus x initial, which is going to be 0 minus 0, or he has 0 meters of displacement. Even though he's gone a full mile, I think those horse tracks are a mile roughly, even though he's traveled a full mile, he has a displacement of 0 meters. All right, we'll talk about that in just a minute. Let's do some more examples. Let's say that we have this graph of position, and then I want to move from one point to another for different initial and final positions. I want to calculate what is our displacement. So let's say that I go from an x initial, I don't know, say from -1, that's our x initial, to our x final of 3 meters. Then what is our displacement? What is our displacement if I move from an x initial, an initial position of 1, or -1 rather, to a final position of 3? What is our displacement? It's going to be what now? 4 meters, right. So my delta x, or my displacement, is defined as x final minus x initial, and that's going to be 3 minus -1, which is going to be 4 meters. And you notice that I have 1, 2, 3, 4 meters, and then we'll begin to talk about positive and negative directions. Here, this is going to be a positive value. We'll see that when we move to the right, it's going to be positive. When we move to the left, it's going to be negative. I'll write that down in just a minute. Now, let's also think about what if I go from, say, an x final of 2. So say from this position, this will be our x final, and then x initial, say, will be -2. So what is going to be our displacement in that case? It's also going to be 4. I say I have x final minus x initial, which is going to be 3 minus -1, or 3 plus 1, which is also going to be 4 meters. And then finally, we can also say, what if my x initial is 4, and my x final is -3? Then what is my displacement in that case? Well, our delta x is x final minus x initial. That's -3 minus +4, and so that's going to be -7 meters. And so that gets us into the idea that displacement then is a vector. And vectors have both a magnitude and a direction. And so you remember when I told you that we used a right-handed coordinate system, right? In our coordinate system, we have different coordinates. We have our plus x and our minus x, our plus y and our minus y. Well, in these coordinate systems, these signs, the plus and minus signs, indicate direction. Now, as far as we're concerned in this chapter, we're only going to have one direction. That's why it's one-dimensional kinematics. In the next section, in chapter 2, we'll deal with two-dimensional kinematics, and it gets a lot more complicated. Well, not a lot more complicated, but a little more complicated. So if I have a displacement vector, say I have a delta x equal to -2 meters, the direction is negative, and the magnitude is 2. This direction, since it's x, it's horizontal, so I can say that this refers to a left direction. If it was a y variable, then it would be up and down. What would my negative indicate? If it was a y variable, now if it's x, the negative indicates left in that direction. But if it's a y variable, what does it indicate? A negative. it indicates downward motion because negative y is in the downward direction. Sometimes we're going to give direction in other ways. Like, for example, we might use cardinal directions. You guys will do this in lab, I think not this week, but next week. You're going to do vectors. I'm pretty sure it's the third lab, where you'll do 2D vectors, and you'll look at vectors in terms of their cardinal directions. And so, for example, let's say that I have my compass rose, where I have north, south, west, and east. Isn't that right? North, east, west, south? Yeah. I might have a direction that is, say, 30 degrees north of west, in which case I'm going to have a vector that looks like this. It's going to be 30 degrees north of west. This is not important in this chapter because we're only dealing with 1D vectors. But in the next chapter, we'll do 2D vectors. It will be important. And you could see some cardinal directions. Vectors represented by cardinal directions, north, south, east, west on the test coming up in a couple of weeks. Some examples of vectors, things that have both magnitude and direction. Well, displacement is a vector. Velocity is a vector. Acceleration. We have other vectors too, though, that we'll see this semester. Forces, momentum. We'll see vectors sort of come up throughout the semester. We usually show the variables for vectors with an arrow. So, for example, if we have a displacement vector, we'll put an arrow over the top of it. Or if we have a velocity vector, we'll put an arrow over the top of it. Or a force vector, we'll put a little arrow over the top of it. In other classes, you might see slightly different variations of this. Like, for example, you might see, not in this class, but in other classes, you might see a little hat. And that also indicates a vector. Or you could see a slightly different arrow, maybe just with one line with a little tail on it like that. So you can see variations of the arrows. Honestly, I'm going to get a little lazy with my arrows, like when we get into kinematics, because we'll just be sort of writing a lot of X's and Y's and A's and B's. But it'll always be implied that we're doing vector quantities. On the other hand, so we have vector quantities, and then we also have scalar quantities. And scalar quantities only have a magnitude. They only have a magnitude. I mean, they have no direction. Can you think of some scalar quantities that you measure? Hold on just a second. Or do you have a question? You're going to answer. So displacement is a vector quantity. Sort of the analog to displacement is something that we call distance. So displacement and distance are related in a sense that they describe how things move through space, but distance is different in that there is no direction. And so, for example, and you'll see some questions on the homework test, on the homework assignments on Tutor coming up soon. If I go back and think about this Seabiscuit, or this horse racing around the track, this guy has a displacement going from 0 to 0 of 0 meters. But he's traveled a distance of 1 mile. So here the distance that he's traveled, which is the magnitude, or rather is sort of the over the land travel that he made, is 1 mile. Even though his displacement is 0 meters. Okay? It's sort of a nuanced difference, but it's an important difference. And it'll come up on your homework assignment, and it'll probably come up on your test too. All right, so some scalar quantities. Blair, right? You have one? Okay, yeah, speed. We're going to see this soon. Velocity is a vector quantity that describes how the position changes with time. And speed is kind of like how distance is to displacement. Speed is as it is to velocity, like it's the magnitude of the velocity. Are there some other scalar quantities that you can consider or you can think of? Yeah, time is a scalar quantity because it doesn't have a direction, it just sort of proceeds. One more maybe? Mass, right, that's the one I was looking for. So mass is also a scalar quantity. There are some other scalar quantities like charge and temperature as well. Length is a scalar quantity. Usually, we usually consider length to be a scalar quantity. So let's try this little quick test. This was from an old test, so hopefully this is a question that everybody will get right on the test. Which of these is or are scalar quantities? By the way, get used to these types of questions because I like to give them, that is the type where I give you several options and you have to pick the combination of options. Just get used to it so maybe you haven't seen those before, but I give those a lot. All right, we'll stop at say 33. Oh, y'all are awesome. Good. All right, so 33. Look at that. That's what I like to see. 100%. I would love for everybody to make 100% on that first exam. Like it would just really set us into the semester with a good tone for the first exam, set you up well for the upcoming exams. Okay? All right. Oh, let's see. What is the worst part about living on O Street? You gotta walk a whole block to pee. Do you get it? Y'all get it? Okay. Sorry, that is a little 5th grade humor for you. All right, so let's look at velocity and speed. Somebody, I think, Blair, I think, mentioned that speed is a scalar quantity. So like displacement and distance are similar in that way that they're related. They talk about how the position changes with time, or how the position changes as an object moves. Velocity and speed are similar. Speed is a scalar quantity. It is the magnitude of the velocity. And if we talk about our average speed is the distance over time. Right, so like if you cycle or if you run, you have like a GPS, right? It can tell you what your average speed is, or it can even tell you your pace. It's not telling you what your average velocity is, or it doesn't tell you what your displacement is, because that would always be 0, because you always come back to the same spot, almost always. It tells you what your speed is. It doesn't matter about your direction. It only matters the distance that you've actually traveled. We could also write this as V is distance over time. We often use D for distance. I'm not sure why. And the way that we would differentiate this speed from velocity is that there's no arrow on top of it. You'll get the hang of it. It's not going to be a big deal. If it seems confusing to you now, don't sweat it. All right, so if a runner traverses a 400-meter track in 60 seconds, what is her average speed? So go ahead and calculate her average speed. I'll give you just a few seconds and I'll jump in there. What is the average speed of this runner that goes around a 400-meter track in 60 seconds? Alrighty, so if I wanted to calculate the average speed, I'd just say the distance divided by the time. That distance is 400 meters, and the time is 60 seconds. That's 40 over 60, which is about 7-ish meters per second. The distance covered here is 400. Right, that's the actual over-the-ground distance that she covers. But her displacement, then, as we talked about before, is 0 because you're beginning and ending at the same spot. Although, of course, on a track, you don't begin and end at the same spot, 400. But there's imagine that that's the case. All right, now let's think about average velocity. Average velocity is going to be our displacement divided by our time. It is a vector, so it has both direction and magnitude. And since it's displacement over time, that's going to be our delta x over our time, our elapsed time. So if I wanted to calculate the average velocity of the young woman in the previous problem, I would say that the average velocity, either with an arrow, or sometimes we do average velocity with a bar over it. I'm going to do it as an arrow here. That it is delta x over delta t. And so that's going to be 0 meters minus 0 meters divided by 60 seconds. And so that person has an average velocity of 0 meters per second. Okay, because the displacement was 0. Y'all with me on these? We're really just sort of making definitions. Yeah? Okay. All right. Let's look at plots. You're going to see a lot of plots on the next test. They're kind of useful to help you to visualize what things are doing. And just being able to interpret plots is a useful skill for you guys as scientists as you move into biology or the health sciences. And so you'll see a lot of plots because, I don't know, I like them. They're important for you. And so let's consider this plot of position versus time. What I have here is the x position on the y-axis and the time on the x-axis. Right, this is our independent variable. T is independent. It changes independent of the other variable. This is our position. It's our dependent variable. It changes in response to time. This variable depends upon this variable. At a given time, I can figure out the position. So if I want to know the position at 10 seconds, I say, oh, the position is 0. If I want to know the position at 30 seconds, I say the position is 40. So I can just read off information from that graph in that way. The slope of this graph is very important. The slope of this line gives something from over a certain time interval. What would the slope give? You're going to see this. In fact, you have a lab this week where you deal with slope in the physics lab. And so whenever you're dealing with slope and you want to know what the slope represents, I always like to look at the units. So what would be the units of the slope for this graph? On the y-axis, I have x, which is in meters, and on the y-axis, I have t, which is in seconds. What are the units of that slope? How do we find slope? First of all, it's what over what? Rise over run, right. So it's the change in y over the change in the x-axis. So my y-axis has meters, right, divided by seconds. So the slope of the line is going to be in meters per second. And so meters per second, that's our velocity. So the slope of the line gives the average velocity over the time interval from t equals 0 to 30 seconds. So you can do this work down here, but I'm going to do it up here where you can see the graph. If I want to know the slope of the line between t equals 0 and 30 seconds, then I'm going to do my rise over my run. My rise here is, it goes from negative 20 to 40. So that's going to be 60 is my rise. That's my delta x, my change in position. My run is going to go from 0 to 30. So it's going to be 30 is my delta t. So if I want to know my average velocity, it's going to be delta x over delta t, which is going to be 60 over 30, which is 2 meters per second. I can put a positive there because it tells me that it's in the positive direction, my average velocity. Notice here that the slope of this graph, is it positive or negative, the slope of the graph? It's a positive slope, right? A positive slope looks like this. A zero slope looks like this, it's flat. And then a negative slope looks like this. So if you're not familiar with sort of dealing with slope, hang on, because we're going to do a lot of graphs. And you'll be good at it by the end. Okay? I could also take the average slope over other intervals. Like for example, let's say that I wanted to take the slope over this interval from point A to B. My time would be 10 seconds. My my displacement would be, well, it's going from negative 20 to 0, so it would be 0 minus negative 20, which is equal to 20. And then if I calculate that average velocity, it's also going to be 2 meters per second. That is 20 divided by 10. The slope of this line is also 2 meters per second, just like the slope of this line is 2 meters per second. Hopefully that's somewhat clear to you. See that? Okay. So because the line is linear, right, a graph that looks like this, that's a linear graph. A graph that looks like this, that's not a linear graph, that's nonlinear. And we'll deal with the latter part soon. But because this line is linear, it's a straight line, and the velocity doesn't change, the average velocity from, say, 10 to 30 seconds is the same. That average velocity would be delta x over delta t. Well, you just take a moment and try to work that out. Well, I'll show you actually. From 10 to 30 seconds, this is going to be 30 minus 20. This is just like what we did on the previous when we went from A to B. But here we're going from B to C on that graph. So it goes from 30 minus 10. And then on the numerator is going to be 40 minus 0, which is going to be 40 over 20, or 2 meters per second. The velocity is the same. All right? Y'all with me, folks? Listen, if you're feeling left behind at this point in the class, then by all means come see me, because I can help you get back on track, okay? I know that there are some of you in the class right now that are feeling a little left behind, like you're not really getting this, but by all means, please come see me, because I can help you get back on track. And now is really the time for you to come see me, not in a week or 2 weeks or even 2 months. That'll be too late. But if you come now, we can help you get on track, okay? If you don't want to come see me because I'm mean or whatever, and I can be mean, I understand, but the tutoring center has other students that can help you as well. They're really cheap. Usually tutors are $20, $30, $40 an hour. I think it's like $25 a semester. Am I right about that? Tutoring center is really great. The tutors that they have are students that have made A's in this class, so they can really help you with the class and give you hints and tips on how to do well in the class. Okie dokie? All right, lots of good resources for you to use. Also, just a little hint. I know that many of you are really good students, but some of you are kind of like me, where you're just sort of a ho-hum student, right? Some of you are ho-hum students. Maybe, maybe not. But it's a good practice as a student to be working on things every single day. And I try to give you assignments to help you, prompt that, like the tutor assignments and coming to class and all. But every day you really need to spend 15 to 20 minutes working on stuff outside of class. I think 15 to 20 minutes is a good fare. If you have sort of solid math skills, then 15 to 20 minutes. If that's not the case, then maybe longer. Okay? If you need help with your study skills, come see me. I can sit down with you. I can help you sort of formulate a plan for all your various classes. Or also go to the tutoring center. They do that there as well. But they might be mean sometimes too, just like me. And if they're ever mean to you, you just come see me. All right, let's see if the graph of this velocity of the object varies with time. Oh, in this graph, the velocity of the object varies with time. So, before we had a straight line, so the velocity was always the same. But in this graph, the slope changes with time. Sometimes it's big, sometimes it's small, sometimes it's negative, positive. So the average velocity depends very much on the chosen time interval. So let's consider that we wanted to find the average velocity from t equals 0 to t equals 10 seconds. So our average velocity is delta x over delta t. Delta x is x final minus x initial. And then delta t is going to be, well, it's just going to be t, because our initial time is 0. Our x final is the position at t equals 10 seconds. So that's going to be 30 meters. Our x initial is going to be at t equals 0 seconds, so that's 20 meters. 30 minus 20 meters, and then divided by 10 seconds. And so that's going to be 1 meter per second. So if I were to draw a line that went from here to here, it would have a slope of 1. And actually along that function, that line is pretty linear. That part of the function is fairly linear. From 10 to 30 seconds, on the other hand, if I look at that, going from 10 to 30 seconds, that's from here down to here, what do you think the average velocity is going to be? Is it going to be positive, negative, or 0 from 10 to 30 seconds? It's going to be negative. Because if we look at this line, the green line here, the slope of this line is negative. Remember? Positive, 0, negative. So the slope of that line is negative, and then we can calculate what is the average velocity. In a similar way, we say delta x over delta t. It's going to be minus 20 minus 30 divided by 30 minus 10. This is in meters, this is in seconds. Let's go back and I'll show you where I got that. So I have minus 20, which is right here, minus positive 30, which is right there, so minus 20 minus 30, and then the time is going to be 30 minus 10. That's going to be 20 seconds. All right, so this is minus 50 over 20, which is minus 2.5 meters per second. But keeping proper sig figs, I do minus 3 meters per second, because I only have one sig fig in all those values. Okay? You're going to have a graph on the test, and I'm going to ask you several things about it. And one of the things that I'll likely ask you is, what is the average velocity between this time and this time? That's all you do. You pick the data points off the graph, and then you take the ratio of delta x to delta t. What is delta x over delta t? All right. By the way, you will see an equation sheet online on the website. I mentioned this to you last week, but just to be clear that there will be no equation sheet on the exam, on this first exam. There's really only 2 equations, except for your trig functions. There's really only 2 equations, so, you can imprint that on your mind pretty easily. All right, instantaneous velocity. So v is the velocity at a particular instant, or a particular time. At a particular instant. When I say v, I'm talking about the instantaneous velocity. So this will be sort of the typical velocity that we'll use. So anytime I say velocity, henceforth and forevermore, I will be talking about our instantaneous velocity. If ever I want to know average velocity, then I'll say average velocity. But instantaneous, I don't know, it's a bigger word, so please don't say it. Okay? So v is our velocity at a particular instant. So for example, a speedometer in your car gives the magnitude of the instantaneous velocity. It gives the velocity at a particular instant. It doesn't give you your average speed over an interval of time. Instead, it gives you that velocity at that particular instant. Actually, to be honest about it, your speedometer does give you an average speed. You know this? But what time interval does it give you that average speed for? Is it a long time interval or a very short time interval? A very, very short time interval. And so whenever I want to know my instantaneous velocity, all I do is I figure out my average velocity, but over a very short time interval. That short time interval is an instant in time. So you just make that time interval really, really short. Y'all follow me? Good. So you follow differential calculus. That's all differential calculus is that it takes that thing in the denominator, in this case delta t, and it makes it really, really small. That's how we define what a derivative is. And so even though you're not required to have calculus for this class, I know that many of you do, and you're never going to see calculus on the exam in any form or fashion, but it's important, or it's useful, I think, for you as you're studying differential calculus, as many of you are right now, that you understand how this relates between velocity, distance, or displacement, and time. And the velocity, the instantaneous velocity, is the limit of the average velocity as delta t gets really, really small. That's just like in your car. The speedometer reads the limit of delta x over delta t as delta t gets really, really small. Tell your friends that, and they'll think that you're really cool. Just as you're driving down the road, say, hey, did you know that this thing gives the limit of delta x over delta t as delta t approaches 0? See, you guys are going to exit from this class. Yeah, I can even see it right now. You're going to walk out that door cooler people than when you walked in. Because now you know these things. That your speedometer is actually doing a derivative. And that's kind of cool. All right, so that delta x over delta t, we just let this get really, really small, and that is our derivative. So this is a derivative. In a nonlinear graph, such as this one I'm going to show you down here, the slope of the tangent line is equal to the instantaneous velocity. So remember when I write this, this is instantaneous velocity. Okay? So students often have trouble with the tangent line. Knowing what a tangent line is. There is a mathematical definition for a tangent line, but I'm not going to show it to you because I always like to sort of think of it as if I have a ball like this and I put a seesaw on it or try to balance a board on it like this, that board represents the tangent line to that curved surface. The mathematical definition has to do with the distance between different points on the board and the curved surface. But you basically want to balance your tangent line onto your function. So for example, if I wanted to draw the tangent line on this function, at this point, I would draw a tangent line that looks sort of like that. You think of it as being balanced on that function. That it was balanced on this function and wouldn't tip one way or the other. So for example, at this point, my tangent line would not look like this. That's not my tangent line, right? It's not balanced on that. Likewise, it doesn't look like this. It's going to balance right on the edge of that function. Okay? So if I want to know if I have a function like this, and you will on the test, you most definitely will have a function that is nonlinear, that is a position versus time graph, and I'll ask you what is the instantaneous velocity at a particular time. You'll draw a tangent line, like this one, and then to find the instantaneous velocity, you take the slope of that tangent line. So I do my rise over my run, my delta x over my delta t. I find the slope of that tangent line. Let's do a quick test. Look, this was from an old test. Here I want to know what is the particle's instantaneous velocity at t equal 4 seconds. This is a position versus time graph. And I want to know the position versus velocity at t equal 4 seconds at that point in space. You'll need to draw a tangent line at that point, and then you'll need to find the slope of that tangent line, and that'll be your answer. Remember that there are some options here that you can probably just eliminate already. What are the options that you can eliminate already? All right, I can get rid of the negative 2, because I know that this tangent line is going to be positive. I can also get rid of 0 because I know the tangent line is not 0. That it's going to be a positive slope. So there you go, man. 1 and 3. You're already improved your odds. If you finish this problem, go on to the next one. All right, feel free to ask your neighbor what they put if they're uncertain. We'll go about 15 more seconds or so. 220. You're usually wrong, is that what you said? All right, we'll go to 228. 228. Okay, let's see. Y'all put either A or B. Let's take a look. You want to draw your tangent line, and it's a little tricky to get this tangent line just right, but there is a definite answer. I drew my tangent line like this. See how it actually along this graph, the function is actually pretty linear. So it's not even, I don't really have to draw a tangent line. I just sort of draw a line along the function. And then I draw my triangle, and then I try to find out what is my my rise over my run. My rise is 6, and my run is what? What do y'all think? So I know what you did. The students do this. What is the run? What is the change in the time? It's 2 seconds. What did y'all do? Those of you that put D, what did you do? You didn't say the time was 2 seconds. Instead, you said it was, what did you say? 4. You said it was 4, right? Because you counted the squares. Is that what you did? Did you count the squares? It's okay. Just admit. Did you count the squares? Thank you. Thank you, Garrett. You counted the squares. So be careful when you're looking at graphs, because often the squares don't really represent whole numbers. Notice you always have to look at the axes. So the time goes from 3 to 5 seconds, and not over 4 seconds, even though you have 4 squares. So if I want to know my slope here, just to wrap this up, I say 6 meters over 2 seconds, and the 6 meter rise is a positive value, so that's going to be 3 meters per second, which is A. It is not 1.5. When you put 1.5, it's because you counted the squares. Just be careful with that, okay? Students often do that. But I also often put graphs that don't have whole numbered tick marks on the axes. Y'all follow me? Be careful with that. What is the average velocity between t equals 0 and 2 seconds? All right, let's do about 10 more seconds, stopping at 120. 120. Okay, I'm pretty sure B is right. Let's take a look. I want to go and mark, and I'm pretty sure that's right. Between 0 and 2 seconds, I do my average velocity. I'm going from here to here. So that's going to be delta x over delta t. Delta x is minus 4 minus negative 1. And then delta t is 2 seconds. So that's minus 4 plus 1. That's minus 3 over 2, which is minus 1.5. Is that what we put? B was the right answer? Yeah. Okay. You'll certainly have some questions like that. You'll probably see 5 to 7 problems that will have graphs in one way or another. Let's turn to our back in our last 5 minutes. Let's do some clicker questions. So turn to the back of your workbook for chapter 2. There's some concept test questions. We'll fight this. The first one is you and your dog go for a walk. Your dog go for a walk. You're just walking straight line, but your dog is crazy and it's going all over the park chasing after stuff. When you reach your destination, do you have the same displacement? Yes or no? All right, let's stop at 1 minute. 1 minute. Just ask your neighbor if you're not sure. If you're not sure, just guess. 50%. Okay, awesome. A is right because it depends only on your initial and your final positions. It doesn't matter about all that extra stuff that he ran. You have the same displacement. Have you traveled the same distance? No? Tell you a story. My dog, Jolie, she died about 8-9 years ago. But I took her out one day and she was like that. She was running all over the place and there's a river, so she was getting wet and swimming and stuff. And then I was just walking along and I was being a bad owner and just not being aware of sort of her physical limitations. And we got home, she had blisters on her paws. And like the poor girl, she had to lay in a bed for like 3 or 4 days while her paws healed. And I felt really bad. I had to come home and carry her outside to feed. And I had to sort of lay the bowl by her head so she could eat. She was fine after that. She's just puppy. But she was a good dog. Right. Y'all remember Jolie? No, you don't remember. Okay. If the position of a car is 0, does its speed have to be 0? If the position of a car is 0, does its speed have to be 0? Yes, no, or does it depend on the position maybe? Free to ask your neighbor. All right, 50 of you have it right. We'll stop at 48. 48. Okay, good. B is right. Hey, look, think about this graph. Say I'd make a graph of x versus t. I can have a car that's traveling along with a certain speed, and right here it's at a position of x equals 0, but is the speed 0? No, is the slope 0? No, the slope's not 0, so that means the speed's not 0. All right, let's do 1 or 2 more. Does the odometer measure distance or displacement in your car? All right, let's stop it at 28. Awesome. A is right, measures distance. Hey, why can you never starve to death in the desert? Because of all the sandwiches there. Do we have time for another? Oh, let's do this one real quick. Does the speedometer car measure velocity or speed? What does it measure? All right, just a few more seconds. Stop at 22, 22. I know you're itching to go. Oh, it measures speed because it doesn't have direction, okay? All right, y'all have a great day. We'll continue on with this chapter on Wednesday.